Back to my channel Gamma Die Gamma. Today we're gonna do the second part of differentiability. So here's what we're gonna do today. We're gonna be revising the first principle method that I introduced in the last video. So please check that out if you haven't already. And we're gonna build on that, and then we're gonna find some derivatives of functions by the first principle method, which is the way I like to think it is like the definition of a derivative, a classic definition. And then by the end, I am gonna write down a table of important derivatives of functions. And if I have time, I might explore some properties of derivatives. Let's see. And I think that learning this table of derivatives is really important because it will be really helpful in the L'Hopital rule video that we'll be doing. So yeah, let's get on with it. So say we have a function f of x. Then the first principle, the derivative of this function by the first principle at a given point, say x itself, is given by f of x plus h minus f of x all over h. And now I'm considering only the right hand limit of this, because if h is slightly less than 0, then this might just translate to the limit as h approaches 0 of f of x minus f of x minus h all over h. Then again, since we took this negative into account, h has to be greater than 0, because if it's less than 0, then this will just become positive, and then we just get this back. So yeah, and after this, when we are actually deriving the derivatives, I'm gonna be only using one of this. So if it pleases you, I'll just be using the RHD. And if you don't know what this is, please check the last video. This I might leave as an exercise to the viewers, you guys. So you can test yourself by pausing the video if you really understood. Say f of x is something like this. Okay, and you have this point here, say x. So when we are considering the right hand derivative, we are taking a value slightly greater than x. See, this is x plus h, not drawn to scale, please note. Then naturally this is the f of x, and the corresponding point for f of x for x plus h is f of x plus h. And basically, using these 2 points, we are finding the slope, or the equation, or the slope of the tangent line at x. Because we need 2 points, and then when we take the limit, the edge gets really small, and the change over this interval h becomes almost linear because it's so close to each other. Okay, so this is how it's going to work. And the advantage with the first principle is that we have an x, because unlike the last video where we had to take a point, say 0 or 1, 2, an integer, or any other numerical value, now we can do like a general method of finding the derivative at a given point. And please note, say your function went from the domain is say minus 3 to 3. Okay, just example. Then the derivative, and please note the symbol of the derivative, the f dash, or you can just write this as the df of x over d of x. You don't need to specify the point because it's x. any point is defined over, wait, say, okay, so this is a closed interval. So basically minus 3 and 3 are included, this square bracket here. But the derivative will only be defined on the excluded interval. So, minus 3 and 3 are not included here. The round bracket is for not including stuff. Minus 3 and 3 not included, but like the values between them are included. That's because, at these end points, say at this point, you don't have an RHD, right? Because if you take a value slightly greater than x, say x plus h at this point, so 3 plus h, which is greater than 3, the function is not defined because it's only defined on minus 3 to 3. 3 plus h is going beyond 3. Same thing over here, there's no LHD over here at the end point of minus 3. So yeah, that's a bit of a thing that we need to take into consideration every time. This is really useful when we are doing a mean value theorem. Yeah, I'll be doing a video on that too. Yeah, so before we move on, I'll just write the definition again. So for a given function f of x, the derivative, or the f dash of x, f prime of x you can call it, or I'm just using different notation, df of x over d of x is given by this, the limit as h approaches 0 of f of x plus h minus f of x all over h, which if the function is differentiable, and all these functions are the ones we are going to do, is equal to f of x minus f of x minus h all over h, and we are primarily going to use this. Now I really prefer this notation over here, because it actually gives you an idea with respect to what you're differentiating. So it's basically differentiating the f of x with respect to x, because if you remember our graph, we had x in the horizontal axis, we had x in the horizontal axis and f of x in the vertical axis. So it's partitions of h or separations of h are made on x-axis, right? So that's why it's differentiating with respect to x. So if you do physics, you might have the time on the horizontal axis, so then you're differentiating with respect to time, because then you're making partitions of time where you assume that a given quantity doesn't change much, remains linear. So yeah, so I'm just writing it. This is the Newtonian notation, this is the Leibniz notation. I personally prefer this, but if you're solving problems in like one variable or like one dimension, then even this works. I mean, people just say it's like y is equal to f of x, and just people just write y dash, y prime, and because all the other variables are x's. So yeah. Now I'm going to do like a standard, I'm going to differentiate standard functions with the first principle. So f of x is equal to the sine of x. Okay, and yeah. So df of x over d of x, yeah, I told you I prefer the Leibniz notation, is equal to the limit as x tends to 0. Just substitute the values of x. So here it's x plus h minus the sine of x all over h. And now we can use some trigonometric identities on the top. So this will be 2 cosine of x plus h plus x all over 2 times the sine of this angle minus this angle. So x plus h minus x all over 2 all over h. In case you're lost at this point of time, just what I did there. So I'll just write the formula. So sine c minus sine d is equal to 2 cos c plus d by 2 times the sine of c minus d by 2. See, the order matters in the second expression, because the sine of a negative angle is the negative sign. So be careful there. I just use this O on top. Now we definitely care to simplify the numerator of that limit. The limit as h approaches 0 of cos of, so we're going to have 2x by 2. So it's going to be x plus h by 2 times the sine of x minus x is 0, so h by 2. I'm going to pull this 2 down and you will see in a minute why. H by 2, and please pay attention here that this, because h goes to 0, write it in the bracket, h goes to 0, h by 2 also goes to 0. So it satisfies the identity. The limit is say h approaches 0 of sine of h by h. It satisfies that identity, and this goes to 1. All we are left with is the limit as, so the derivative of the sine of x with respect to x is precisely the cosine of x. And I've only done this for the RHD condition, because I took first the value of sine, where x was, where the value was slightly greater than x. You can also obviously do it for the LHD condition. You have to use the same formula, because it's the difference of two sine values. So you can use the formula in the blue. Definitely do that. You'll end up with the same expression. You'll end up with the cosine of x. Actually showing to you that sine as a function at every point is differentiable. So we don't need to worry about that, because if it weren't, then you have an x value which did not satisfy this equality of the RHD and the LHD. So yeah, you can, if you want to pause, you can try the LHD question on your own by pausing the video. Let's do another trigonometric function. Say the f of x equals the tangent of x. So the derivative of the tangent of x with respect to x is the limit as h goes to 0 of the tan of x plus h, again the RHD condition, tan of x all over h. Now we don't have an official formula. I mean, I don't use a subtraction of tangents formula. What I do in cases when I have a question like this is I break the tangent into sines and cosines. So the sine of x plus h over the cos of x plus h. I hope you know this identity. This is the most basic identity that you can come across when doing basic trigonometry. All over h. Just written the tangents and tangents as ratios of sines and cosines. The limit as h goes to 0. Now we can totally cross multiply this thing. So the cos of x times the sine of x plus h minus the sine of x times the cosine of x plus h all over cosine of x times the cosine of x plus h times h. If you want, I can bracket this out. Now looking at this, you probably might have guessed that we can use this identity of cos A sin B minus sin A cos B as saying sine of a minus b. We can, and we have to, because if you notice all these solving these limits of the first principle, they all require great knowledge and great flexibility with knowing your identity. So so according to this formula, it's basically I'm so sorry, this identity was sine of b minus a. Sorry with that, not a minus b. So according to this formula now, so the sine term minus this cosine, so that this is going to be the sine, and then subtract the angles of the first sine x plus h minus the angle of this first cosine, all over the mesh at the bottom. The cosine of x times the cosine of x plus h times h. So then these x's just cancel out. We have the limit as h goes to 0 of sine of h over h, and I'm going to split this into two products. The limit as h approaches 0 of 1 over cosine of x times the cosine of x plus h, and this just goes to 1. Don't even need to change the variable or something. So and when we substitute h as 0, we have 1 over the cosine squared of x, which is also can be written as the secant squared of x. So there we have it. The derivative of the tan of x with respect to x is the secant squared of x. So let's do some exponential functions now. Enough with the trigonometry. And this is probably the easiest function you might come across. Its derivative is very simple to calculate. So the limit as h approaches 0 of e raised to x plus h minus e raised to x all over h. Now, if you know some exponential properties, this is e raised to x into e raised to h minus e raised to x all over h. And since it's a multiplication in the numerator, we can just factorize e raised to x out. E raised to h minus 1 all over h. And again the identity, this thing will just go to 1. And since there is no h term now remaining in the e raised to x, the limit as h tends to 0 of e raised to x is just e raised to x. It's actually a fascinating result. The derivative of e raised to x with respect to x is e raised to x. And it's the only function whose derivative is itself. So and this result is important if you're going into differential equations and integration stuff. Very useful. Speaking of exponential functions, let's take an arbitrary base and raise it to x. So derivative of a raised to x with respect to x is going to be the limit as h tends to 0, a raised to x plus h minus a raised to x all over h. Now I won't write it as a product, I'll just factorize it out. A raised to h minus 1 all over h, and this doesn't go to 1, but instead it goes to the natural log of a. This is going to be a raised to x times the natural log of a. And no h terms now, it's just a constant now. A raised to x times natural log of a. That's the derivative of, let me write it down officially. So d over dx of a raised to x is just a raised to x times the natural log of a, and it actually makes sense because when a was e, then you'd have e raised to x times the natural log of e, and the natural log of e is just 1, so e raised to x makes sense. Everything just fits together. Now let's move on to a logarithmic function, the natural log of x. D over dx of ln of x is the limit as x tends to 0 of the natural log of x plus h minus the natural log of x all over h. And if when you are subtracting two natural logs, you're basically just dividing the arguments with each other. So x plus h all over x by h. I'll probably write the formula here. So log a minus log b equals log of a per b. Yeah, you can just clean up the numerator a bit. So the natural log of 1 plus h by x all over h. Now if you the identity went like this. So we had the limit as h goes to 0 of log of 1 plus x 1 plus h here, let's say, by h. This went to 1. So basically this the quantity after the which is added to the 1 should be the same as the denominator, but the quantity here is h by x. We can introduce an x because now x is a constant because the limit is purely in h. So we can multiply and divide by an x in the denominator, and can separate things out. The limit as h goes to 0 of the natural log of 1 plus h by x all over h by x is genuinely 1 because when h goes to 0, h by x also goes to 0, x is a constant. And x is not 0 because then it's evident because the derivative is 1 by x. So at x is equal to 0, it's not differentiable. Not differentiable, the derivative doesn't exist. So yeah, let me logically write it down. D over dx of the natural log of x is 1 over x. Now I'll quickly like to do a log to the base a, say, of x. It's variation because last time it was a natural log to the base of e. So d over dx of log to the base a of x is the limit as h goes to 0 of log to the base a of x plus h minus log to the base a of x all over h. Again, see the the identity before log of a minus b is equal to log of a by b. That holds for any base. So log to the base a of 1 plus h by x all over h by x times x. Just doing it like before, multiply and divide by x. But the limit identity that we wrote before, say the limit as h tended to 0 of ln of 1 plus h all over h is equal to 1. That's only true for the natural log. I think I just written a log for when we were differentiating the last function, but it is only for the natural log. I repeat, it's only for the natural log. So here we're gonna have to change the base. So this is gonna be um, the natural log of 1 plus h by x all over the natural log of a divided by x into h by x. And okay, I'll just clean this up. So I'll just pull the x times natural log of a outside, because not they do not depend on h. The limit as h goes to 0, natural log of 1 plus h by x all over h by x is 1 according to the identity, and x is not equal to 0. And finally, nothing depends on h anymore outside, so this is going to be just be 1 over x times the natural log of a. Let me properly write it down. D over dx of log to the base a of x is equal to 1 over x times the natural log of a. And in case you are wondering how we change the base, here's the change of base formula. So you have, see, a log of b to the base of a. You can write this as log to the any base. Let's say take 10 to the base of b, so the top with the in the numerator, divided by the log to the base 10 of a in the original base. So I just converted from base a to base e. That's why we have this natural log popping up. I would quickly like to do an inverse trigonometric function. I know you guys might not be so familiar with them. We didn't do any limit identities with them, but so yeah, let's go. D over dx of tan inverse of x is the limit as h goes to 0 of tan inverse of x plus h minus tan inverse of x all over h. Yeah, so now there's an identity. First, let me just write the numerator according to the identity as x plus h minus x over 1 plus x times x plus h all over h. It's all about identities, and see, we have tan inverse of x minus the tan inverse of y. You can write this as the tan inverse of x minus y over 1 plus xy, where xy is, I think, greater than 1. You might want to check it up. So yeah, I've just used this formula. You might want to check the condition again. I won't guarantee, but for all our purposes, we can just use this. So the limit as h tends to 0 of cancel out some x's. See, the tan inverse of h over this craziness, x square plus hx all over h. Now, since I'm well averse with the limits on inverse trigonometric functions, I'll just multiply and divide by the base, the denominator of the argument. So this thing times 1 plus x squared plus hx. And you might be like, why did I do that? Because there is this identity, the limit as z goes to 0 of tan inverse of z over z equals 1, just like its counterpart of the tan, because we had the tan of say x by x is the limit as x approaches 0 is 1. So just like that, you can totally prove it. You can prove this thing by the tan, by the identity on tan. You can do a variable substitution. So I'll just quickly do it. So let z is equal to say tan theta, okay, and when this is a z goes to 0, tan theta will also go to 0. This is a 0, yeah, and then this thing will just become the limit as say tan theta goes to 0 of say theta over tan of theta, and as see tan theta goes to 0, even theta will go to 0. So overall this identity is again satisfied. The tan identity is satisfied, and you just end up with a 1. Tan theta goes to 0. Theta will go to 0 because when tan theta is really small, both of these behave similarly. Just like the sine theta by sec theta, you can make an approximation of this size. And when h goes to 0, this entire argument goes to 0, because in the denominator you have 1 plus x square, and this thing will go to 0. So you have 0 over something which is 0, and again here it's 0 because the argument and the denominator match. So this entire thing will go to 1, and all you're left with is the limit as h approaches 0 of 1 over this crap, 1 plus x squared plus hx. And when you substitute h as 0, this thing will just go away. You're left with 1 over 1 plus x squared. So officially d over dx of the tan inverse of x is 1 over 1 plus x squared. Now finally we have a table of derivatives. So we start with say like a quadratic function. I think I should have done this, but it was finding the derivative of x squared by the first principle is easy. You have x plus h the whole squared, and then you expand the bracket, and then so the x squared terms cut out and simplify. You can do it on your own also. Is 2x, and in general, okay. So first, let me give you some more examples. So x cube is 3x squared. You might have realized that the derivative of x raised to n is just n times x raised to n minus 1. It's true for even say fractional powers. So you have x raised to half will give you 1 by 2 times x raised to minus half. Probably write that down. Know this, it's a good thing. 1 over 2 times square root of x is same, square root of x is just x raised to half. And then you have these trigonometric functions. The sine of x is cosine of x, and the cosine of x, it's a silly thing, but it's the sine of x minus sine of x. Then if you have the tangent of x, and we just proved it, it's the secant squared of x. If you have the secant of x, it's the secant of x times the tangent of x. And if you have the cotangent of x, it's the negative cosec squared of x, you have the cosec of x, you have negative cosec of x times the cot of x. E raised to x is just itself. E raised to x is e raised to x times the natural log of a. Natural log of x is 1 by x. Log to the base a of x is 1 over x times natural log of a, and this is in the denominator, put a bracket like that. Say ITF, inverse trigonometric function. So tan inverse of x, we did this 1 over 1 plus x squared. Sine inverse of x is 1 over square root of 1 minus x squared. Cos inverse of x is the negative of this, 1 over negative 1 over square root of 1 minus x squared. Then if you want, sec inverse of x is 1 over square root of x squared minus 1. And the cosec inverse of x is just the negative of that, minus 1 over square root of, x times the square root of, minus x times the square root of x squared minus 1. And if you I'm just writing it up, the derivative of a constant is 0. Derivative of x is 1. So yeah. So this table is very important because we're going to be doing L'Hopital's rule in probably like the next few videos, and I promise, because now we've done differentiability, right? We just need to know the derivatives of some function, L'Hopital rule, and for the limits in L'Hopital's rule, the questions, we just require some simple formula, like this formula is really important. You might not want to do the inverse trigonometric functions because probably you haven't studied them deeply, but these trigonometric ones are important, so I would recommend noting it down and learning like the important ones at least. And yeah, the exponential ones also very handy. Log functions, yeah, important too. Inverse trigonometric functions are a speciality. If you can do it, it's great. Otherwise, leave it for now. This is an important property. I might be covering it in properties, and yeah, I'll do properties in the next video because I think we've gone a little bit over time. So yeah, I guess that's it for this video, guys. Please like, share, and subscribe. If you have any doubts, you can always comment in the comment section below. Have a great day. Peace out.